Hi everyone, my name is Dunya Ghazia and today I'm gonna present a paper, Hypercube High Dimensional Hypervisor for Fuzzing. I just need to make sure that it's recording. And this paper, yeah, okay. So this paper is basically was published in NDSS Symposium 2020. Let me tr like go with you through the agenda of today. I'm gonna just start by explaining some foundational concept just to set the stage about everything and make sure that all of us on the same page on the whole concept that I'm gonna present in the paper. And then I'm gonna explain some introduction and background about the topic or the idea of the paper and go through the design and implementation and then the evaluation, and I'm gonna end with some discussion and future work for this paper. So let's start by a foundational concept. What is a virtualization? I believe that all of you are already aware with what is virtualization, but just in case, it is basically allows multiple operating systems or VMs, virtual machines, to run on a single physical machine by basically abstracting the hardware resources. So virtualization have many benefits over the years, like cost, recovery, management, and so forth. That is why all people nowadays are taking care of virtualization security and giving it too much thought. Also, virtualization has many types, such as hardware, application, server, network, and so forth. So now I said VMs. So someone might ask, okay, how virtual machines work and how it's gonna how it's related to what I'm gonna talk about today. VMs basically do not directly access hardware, and instead they interact with a virtual machine monitor, which or what it is famous for, hypervisor, which manage basically access to CPU, memory, and other devices, as you can see on the physical server. Okay, now I introduce another new concept, which is hypervisor. Someone might say, what is hypervisor, or at least why it is important in our topic? Hypervisor is basically the software layer that manages multiple VMs on a single machine. It ensures isolation between the virtual machines so that they cannot interfere with each other. So basically, we have two types of hypervisor. Um, like type 1 and type 2, only two types. Type 1 is basically run directly on hardware, which is the bare metal, such as KVM, and type 2, it runs inside an OS, such as the famous VirtualBox or VMware Station, and so forth. And so forth. Which one is more secure? It is basically type 1 is preferred for cloud security because it reduces attack services. Um, okay. So basically, the hypervisor is an important topic in this presentation, and I'd like to explain to you the key communication interfaces between the VM and the hypervisor. So basically, the first one is explained in this table, the memory mapped I/O input output, which allows the VM to read or write memory regions mapped to virtual hardware devices, and the port mapped I/O, it uses special CPU instructions such as input in or out to send data to I/O ports. And the direct memory access, the DMA, it allows device directly to read or write memory without involving the CPU. And the hypercalls, it is similar to system calls but used by the VMs to request the privilege operation from the hypervisor. So basically, why does this matter? It is basically each of these interfaces is a potential attack surface that we really need to take into consideration, that each interface is secure, and we already take care of everything like that. Also, sorry, sorry. Yeah. So now we can ask ourselves, Why hypervisors are a security concern? It is basically, as I just explained in the previous slide, they manage memory, CPU, and I/O, which result in being a huge attack service. And a hypervisor bug can lead to VM escape. So an attacker can break out a VM and compromises other VMs or the host. Cloud providers such as AWS, Azure, and so forth rely on hypervisor. So any hypervisor vulnerability can threaten the entire cloud infrastructure. So basically, the next question we can ask ourselves is how we test them for vulnerabilities and make sure that this hypervisor is already secure. It is by using fuzzing. Okay, so now I introduced fuzzing. What is fuzzing, or what are like the steps for fuzzing? Fuzzing is basically a powerful technique for finding software vulnerabilities. It is widely used for user space applications, and it uses automated test cases that feeds random inputs to uncover crashes and vulnerabilities. So, like the diagram on the right is basically steps for fuzzing. The first initial step is identifying which targets you system you really need to do fuzzing to, and then determination what are your inputs parameter and generate some fuzzed data, and then execute some test cases with these fuzzed data, and then analyze the results, and then log any issue or any results that you already got from whole this whole process. Um, the problem is or fuzzing the hypervisor is really hard. Why? Because the interfaces must be tested together, not in isolation, in order to like discover vulnerabilities. And also it has high overhead because restarting a hypervisor is expensive, and the regular fuzzer rely on frequent restarts to reset program state. Also, the VM behavior depends on the OS and the hardware state, which complicate the fuzzing results and make them non-deterministic. And last but not least, it is basically the existing fuzzers mostly work on open source hypervisor like QEMU, KVM, and so forth. And this is a problem nowadays because cloud providers use these private or customized hypervisors, which the current fuzzers cannot easily test. Um, so basically, again, why do we think that traditional fuzzers fail to find hypervisor bugs? In order to like ensure, like we already covered this question, let us look into the existing already hypervisor fuzzers. We have like two hypervisor fuzzers, the VZF, which is basically the state of the art, and IO fuzz. So the VDF, it is basically interact only with memory and port managed input output like ports, which makes it low dimensional fuzzing. And the IO fuzz, from its name, we can detect that it is basically randomized IO port testing without the support for any other core interfaces such as MMIO, DMA, hypercolds, and so forth. Also, the test case throughput for the VDF is moderate, and it is really low for IO fuzz. And also the test case, like the stability of test cases, it is somehow deterministic in VDF, and there is it is totally random in IO fuzz. Fuzzing coverage in the VDF is partial because, as I said, it is only interact with memory and port mapped IO, and it is very limited inside fuzzing coverage. Sorry, it is very limited in IO fuzz because it only interact with the IO port. So the gap here is There is no fuzzer efficiently test all interfaces altogether, which, or in other words, there is no multi-dimensional fuzzing, and no fuzzer achieves high test case throughput, and no fuzzer is designed for both open source and customized hypervisor. So, given these challenges, do you think current hypervisor can effectively like test hypervisors? So the answer is like basically no, and we need a new fuzzer for the hypervisor to bridge the gap that the existing fuzzers have. So we need to be able to interact with all interfaces at once, not in isolation, and we need to have some structured test cases, and we need to be able to restart um, restart the system quickly, and we need to minimize the coverage range as much as possible. Simply, we need something to target the hypervisor behavior. That is why this paper already introduces something called the hypercube. It is a novel approach and high dimensional fuzzing. Here is how it works. Um, Hypercube is basically, in a nutshell, generates test cases using bytecode. Bytecode interpreter, which is like the tesseract interpreter, that interacts with multiple hypervisor interfaces here, and then the fuzzer execute these cases while monitoring responses for crashes or anomalies. When an issue is detected, it logs and reproduces it. The system quickly reset using efficient snapshotting and enabling high throughput fuzzing. So now we can see Hypercube is not just a fuzzer, it is fundamentally a new approach to test hypervisor effectively. Now let's like try to dive deeper into how it works. Um, Before like going into the design, let's like set the stage on our threat model. So basically, the threat model is the attack has full control over the guest OS, which is inside the VM. And the goal is to escape the VM to compromise other VMs or like the host system. And this is relevant in cloud computing scenarios where multiple VMs share the same physical machine. Also, denial of service attack is also a concern because it might prevent the VM control or basically bypassing the load limits. Okay, so let's like talk more about like the architecture, but before that, let me remind you again of the goal of this new fuzzer. It is to have high performance, multi-dimensional fuzzing for both open source and private hypervisor, or like the customized hypervisors. And the approach is basically it to extend the two-dimensional fuzzing or the low-dimensional fuzzing into a high-dimensional fuzzing capable of interacting with any number of hypervisor interfaces in any order. So as you can see in the diagram on the right, it has mainly three main components inside the VM. We have two components, the Hypercube OS, the OS, and the Tesseract interpreter. So this OS is a minimalist OS that executes test cases efficiently, and it has like a scratch memory store to store temporary fuzzing results, and it's also used to enumerate all available core interfaces such as MMIO, IO, DMA, hypercalls, and so forth. And this interpreter, it is basically bytecode based fuzzing engine. It executes randomized but structured test cases against hypervisor interfaces, and it generates modular test cases, making it easier to reproduce bugs and use this scratch region to pass dynamic test data to the hypervisor. And other like host side components, three of them, it is minimizer. It reduces complex test cases to small reproducible crashing program, and the logger to basically capture a hypervisor response and serial communication for debugging, and the decompiler, which basically translates fuzzing bytecode into C code for further analysis and debugging. Um, the implementation of this hypercube system, I'm gonna like briefly try to tell you like present to you the implementation of the OS and the interpreter. For the OS, it is basically written in C and x86 assembly, and it's execute in 32-bit protected mode. So it has like three main process. The first process is the boot process. It is basically loads any peripheral firmware and use the interrupt descriptor table to handle execution exception and interrupt, and to disable the external hypervisor interrupt to ensure uninterrupted fuzzing. And the memory management is basically use like a custom heap allocator, and use like this one-to-one physical memory mapping for essential regions. And the third like a stage is device enumeration. It basically detect the core component and use bus scanning to register device memory region for fuzzing, and actively scan or all I/O ports to discover any hidden emulated devices. That's it for the OS. For the interpreter, it is basically randomized instruction generator for multi-dimensional fuzzing, and it is basically implement opcodes targeting the core interfaces, and use pseudo random number generator for the deterministic test cases execution. On the right, I just like took a screenshot from the paper. With the table of like supported operation. No need to like go over them one by one, but it is basically take all the core interfaces and like do read, write, implementation, modification for them. You can just have a look if you are really curious about how they already implemented each like operation. Now moving to like the evaluation. That's it for the implementation. Now moving to the evaluation. The paper basically answers like ask for basically four questions and answered and try to answer them one by one. So the first question was, can Hypercube uncover new vulnerabilities in different hypervisor? With that like a question raised in the paper, and in order to like answer this question they did like this setup, and this setup is basically tested against these six hypervisor, QEMU, KVM, VirtualBox, ACRN, and so forth. And the result, as you can see here in like the top right, sorry, the bottom right, it was able to discover 54 new bugs across all tested six hypervisors. Actually, 43 of them confirmed CVEs assigned, and basically the types of bugs found with memory corruption, 8 memory corruption bugs, kernel crash, hypervisor deadlock, assertion failure, which basically lead to like hypervisor crashes as and so forth. So the answer of this question, is it able to uncover new vulnerabilities? And the answer is basically yes. So the next second question is, can Hypercube rediscover known vulnerabilities that was already like existing in the previous research? And the answer is yes. They did an experiment and they found that it was able to rediscover known bugs, and was able to find the venom, which is basically a known like vulnerability, and it was be able to find it in only 10 seconds compared to like 1.5 hours in period like in any previous research before. So the answer to that question is yes. It was be able to rediscover known vulnerabilities, which is even in faster like which is even like in less time. So like third question is, how does Hypercube compare in terms of test coverage against existing fuzzer? So in order to like answer this question, it is basically uh, they compared it to the VDF, which is basically the state of the art, as I was like explained to you in previous slides. And if we can look into like the limitation of VDF, as I was explaining, it was targeting only the MMIO and port IO, which is basically missing the DMA and hypercall vulnerabilities. And here it requires like almost 60 days of testing to achieve the results. and because of its like coverage guided approach, it slows down the execution. On the other hand, the Hypercube, it was able to find all VDF bugs plus 5 additional device vulnerabilities, which is in total 9 vulnerabilities here, and it achieved these same results in only 10 minutes. um it is basically because it's multi-dimensional, so it was be able to like explore or like test more interfaces. And the last but not least, like last question is, what is the performance impact of its design, its choices compared to other fuzzers? Like performance, sorry, impact in terms of code coverage, interpreter throughput, cache recovery, memory usage, emulation detection, and so forth. So let's take like one by one. For the code coverage, it measured branch coverage across like Cameo modules, and it achieved higher coverage in all but one case compared to VDF. For the interpreter throughput, it was compared against compiler-based fuzzing, such as CFAFT, and it was able to execute 2,300 more operations per second. The reason behind that is the custom byte code interpreter, basically, which is like the one I explained in the design, was basically significantly faster than C-based fuzzing, such as the ones in CFAFT. And the crash recovery and reboot speed, for here, as you can see here, um, in the minimal Linux boot time was 2.3 seconds. However, the Hypercube boot time was 0.22, almost like 0.22 seconds, which is basically like 10 times faster compared to like the minimal Linux. Yeah, it's version 4.15, but it is like almost 10 times faster. For the memory usage, it was like the Hypercube OS, it was consumed 10 megabyte, and the minimal Linux was consumed 30 to 50 megabyte. But it is like tiny memory overhead compared to hypervisor, so we cannot like really consider that as a huge performance like impact. And last one, the enumeration detection. Enumeration detection here, it is basically was able to enumerate more than 90% of the I/O ports, and actually like 100% of MMIO region detection, um, like by using just like the by using a hypercore. And that's it for like the evaluation. For the discussion, I'm just like trying to wrap up on um I want to like trying to understand that while Hypercube seems powerful from the evaluation section, I need you to understand that it is not perfect. Because on the plus side, it is the first high dimensional fuzzer for hypervisor capable of testing even closed source hypervisors. However, it still requires some manual testing, and it is focused only on x86 hypervisors, leaving the ARM and cloud-based platforms as open question. Also, the primary operating mode with 32 bits, and it lacks 64 bit mode. So, in my opinion, like the future work or what is next for hypervisor, it is one potential improvement is AI driven test case generation. I think it might be able to discover more bugs or like more vulnerabilities, or at least increase the coverage percentage. Additionally, using hardware assisted fuzzing could significantly improve the efficiency. And last one, just expanding this approach to like ARM based, not only x86 and cloud native environment could be like maybe a major step forward and make it more like adaptable in many existing systems. So like in conclusion, or to wrap up, I think hypervisors are vital, but they are still vulnerable. Traditional fuzzing methods are not effective enough. Hypercube offers a new multidimensional approach, finding numerous real world vulnerabilities. And I think that the future of hypervisor security will likely build on this foundation. I think that's it for this paper. Here are like the reference of the presentation or like the paper, and I'd like anyone who might have any question just like ask or put them inside the comment. Thank you so much.